chemistry where it's actually going to be split up into two sections. The first half is all about learning how to write and name these chemical formulas, and then the second half is going to be learning about the different types and mechanisms of reactions that take place all around us. So, if you are joining us here on YouTube, feel free to click on the links just below as we do for every video. There are links, Google Share links, to the slides that we're utilizing for the lesson here today, along with your own copy of notes that you can write on, scribble on, do whatever you need to learn this material the best for you. So once again, we are learning about writing and naming chemical formulas. There are three main types of compounds out there. Ionic, covalent, and acids are what we're going to learn how to write and name today. We're going to kick it off with Ionic. In my opinion, Ionic requires the most. It's got the most different pathways you can take to actually tackle it, and so I think it takes the most time to learn it. So we're going to kick it off with that one. And first, we need a little bit of background. And so what we're going to do is first we're going to talk about the definition of an ionic compound. An ionic compound is always between a metal and a nonmetal. And we learned about where those various elements are located on the periodic table a couple of videos back in Unit 2. But the deal with metal and a nonmetal getting together is they are a match made in heaven. And the reason why is because they want exactly opposite things. Essentially, they complete each other. Now think of these elements as living things. These elements want to be happy. They want to become stable. But not every element gets happy the same way. Just like people, we can learn a little bit from these elements. They are out here trying to get happy, just trying to make it. And so they're going to do it. But every element requires a slightly different method of getting there. And so some elements want to lose, some elements want to gain. Well, what are you talking about, losing versus gaining? The overall picture here is that every element wants to have a full valence shell. And you've probably heard that term in middle school. Valence shell is the outermost ring of electrons in the atomic structure. Right? You probably learned where those are located when you're drawing the Bohr models in middle school. We didn't draw Bohr models so much in Unit 3. Here, they're not totally accurate, as we discussed earlier. But you've probably heard that term. Valence electrons are incredibly important. In fact, they contribute to the most surface-level chemistry activity that we see and witness, and that we're going to talk about in this entire course. It's all because of these valence electrons and how these atoms behave in response to them. So everyone wants to have 8 in their valence shell. There are a few exceptions to that. Some are okay with less, and some are okay with more, but we'll talk about that a little bit later on as well. But it's all based on where they are located on the periodic table. As we discussed in Unit 2 and Unit 3, the elements that are located in the same column with one another are in a family. And these families behave like one another. Just like you probably look a little similar, you probably act a little similar to your mother or father, your brother, your sister. Every element in the same family behaves similarly, and that is because their atomic structures mirror one another. How do they mirror one another? Well, it's not their number of protons, it's not their number of neutrons, it's in how their electrons are oriented. They all have the same amount of valence electrons. So we're going to come back to the slide here in just a second. But let's take a look at this modified version of the periodic table, which shows us what is called the Lewis dot structure for all of these elements. And there's a dot for every valence electron on these elements. So notice the alkali metals, aka column 1 or 1A if we're looking at the representative elements. So these are the 8 most talked about groups of elements here. And so column 1 has 1 valence electron. Column 2 has 2 valence electrons. 3, 4, 5, 6, 7, 8. Logically, they've got that amount of valence electrons. It's brilliant. And these are the 8A or the 8A column groups, aka the representative element groups. Well, keep in mind, they all want to get to 8 valence electrons. Okay, I said there's a couple exceptions to that. The main one being hydrogen. Remember, he's only got 1 proton in his nucleus, so he can't actually handle 8 electrons swirling around him. He doesn't have the strength for it. So he's actually okay with having 2. He's also okay with having none. And so, think about this. What would these elements want to do in order to be happy? Let's take a look at sodium, for example. If he gains 7 electrons, he would be like argon. He wouldn't literally be argon. He would have to gain 7 protons to become argon. But if he gained 7 electrons, he would behave like argon. Or, if he lost 1 electron, he would be like neon. And the reason why is, imagine sodium with 3 electron rings. That's how much it has naturally. But it only has 1 electron on that outermost ring. if it loses that one electron in the outermost ring, well, then it only has 2 rings of electrons. And how many electrons are on that second ring? You guessed it, 8. So this whole family right here wants to lose 1 electron in order to get rid of that outermost ring, so that the second to outermost ring becomes the outermost ring, and therefore they become stable and happy. Why is 8 the magic number? It just so happens that that is the most stable electron configuration. And that has to do with all the electrons being negatively charged. They don't want to actually be next to each other, because, as we said in the last unit, like charges repel, opposites attract. So all these negatively charged electrons are repelling one another as they're rotating around the nucleus, right? And the magic number 8 is what results in the most stable configuration allowed, okay? So this entire family wants to lose 1 electron. Well, what happens when you lose an electron? If I lose something that's negatively charged, I become positively charged. And so all of these alkali metals, whenever they get involved in a compound and they bond to another element, they gain a positive 1 charge. So what I would encourage you to do is take your periodic table that you've been taking notes on and referencing throughout this whole course so far, and I would go ahead and put a +1 charge up here at the top. We're going to put charges for all of these along the top here so that you understand what's going on. It's very important, and it makes all these conversations we're going to have here in a little bit a whole lot easier and more streamlined. So let's look at the alkaline earth metals now, just one to the right of the alkali metals. Magnesium could either gain 6 to be like argon, or, same situation as sodium, he could lose 2 to be like neon. Which sounds easier? Losing 2 is much easier than gaining 6. And what happens when you lose 2 electrons? Well, you have a +2 charge. So we're going to put a +2 at the top. Now we're going to skip all the transition metals for now, and the reason why is because they're a little less consistent. But we'll come back to them not too long down the road in this video. So let's go over to the 3A column. If you're looking it up online, the transition metals are also sometimes known as the B group elements, the B block elements. And so what we are sticking to are the representative elements of the periodic table, the main ones, the most common ones that we're going to talk about. So now we're in the boron family or the aluminum family. Aluminum could either gain 5 to be like argon, or it could lose 3 to be like neon, which sounds easier. Losing 3 is most certainly easier. So when I lose 3 electrons, I have a +3 charge at the top here. Now carbon's family, this is where you truly could go both ways. You could either gain 4 or you could lose 4. So which is better? Well, it's the same amount of difficulty, but really it depends on the situation and it depends on the element here. Carbon is definitely a nonmetal and behaves like a nonmetal. We'll talk about what that means here in a little bit. Silicon and germanium are metalloids, and then tin and lead are very, very heavy metals. So this family, although they're in a family, they're not too consistent with their properties. And so some of you might relate. You feel like you're the odd man out in your family, and that's totally all right. Well, this family, they're not so similar with one another. And so what I would encourage you to do is put a plus or -4 at the top here, because it really does depend on the situation. But when we get to nitrogen's family here, now we only have one route to go. Nitrogen could either gain 3 or it could lose 5, and gaining 3 is certainly easier. Well, now that we're gaining electrons, what charge do we take on? We take on a negative charge. So that's why this family, the nitrogen's family, gets a -3 charge. The chalcogen family, or the oxygen family, is going to have a -2 charge, and then the halogens are going to get a -1 charge. The noble gases, the reason why they are called the noble gases is because they don't need nobody. They're higher up than everyone else. Why? Because they've already achieved happiness. They're stable. Count the dots around all these noble gases below helium. They all have 8 dots. The reason why helium doesn't is because helium only has 2 protons. It can't handle the 8 electrons flying around. It doesn't have the strength to do it. But it's okay. It's totally happy. It's completely stable. Another term that you might hear associated with these noble gases is inert. That means they don't react. And so we're not going to see them too frequently in these formulas because they don't want to react with anything. And so the noble gases do not get a charge. So now, let's look at the overall charge of these compounds. Let's talk about a little chemistry. Let's talk a little bit about love. Okay? What's actually occurring here? Well, we said an ionic compound. An ionic compound is always between a metal and a nonmetal. More specifically, the metal More specifically, the metal is going to give electrons, and the nonmetal is going to receive electrons. Why? Well, it all has to do with their positioning on the periodic table. So let's just say that, I'm sodium, and I'm looking for love. I'm looking for someone I can spend the rest of my life with. I've tried all the websites. I've done farmersonly.com. I've done blackpeoplemeet.com. Nothing has worked for sodium. So he goes to the food court at the mall, and he spots a beautiful element across the way. Claretta is her name, Claretta. He couldn't see a name tag or anything like that. He wasn't, stalking with her preemptively. He introduced himself. He discovered her name was Claretta. Okay, this was not creepy in any way. This was a completely organic, blossoming relationship. But anyway, Sodium goes up to Claretta and he goes, listen, I don't know if you're free today, but would you like to split an Annie Ann's pretzel? And she, obviously noticing that Sodium is just an absolutely dashing individual, and says, why, yes, I think my day just cleared up. Let's do an Annie Ann's pretzel. And this is no ordinary pretzel, people. I don't know if you've ever had an Annie Ann's, and let me know if this is completely new. If it is completely new, then this is the first you've heard it, and Annie Ann's needs to call me up and get a sponsorship going here, because I'm talking, this is a hybrid pretzel. It's got the savory on one side, it's got the sweet on the other. What am I talking about? I'm talking about Parmesan crusted on the left half, cinnamon dusted on the right half. And I want two dipping sauces on the side. Maybe a little cheese sauce for the savory, and like frosting for the sweet. Are you kidding me? Who wouldn't bite into that? It's warm, it's savory, it's sweet, it's fresh. Are you kidding me, Annie Ann's? Call me up. Let me know. But anyways, while they're sharing this pretzel, of course 50-50, they're exchanging conversations with each other. They're learning a little bit about each other. And Sodium is just all in the back of his mind. There's something weighing on his chest. But of course, they love their time together, so they go on a second date. They go to the movies. And this is a few days later. But then after the second date, Sodium is walking Claretta home, and he says, Claretta, listen, this is a little fast, but there's something weighing on my chest. I felt like there's always been something extra there that didn't belong. And I just really need to get it off my chest. And Claretta said, oh my goodness. This is exactly what I've been wanting. I am ready. Open up to me. I'm ready. Whatever it is, I can handle it. And so Sodium takes this as the green light. He gets down on one knee and he pulls out a box. But inside the box it's not a ring, people. What is it? It's an electron. Sodium wants to get rid of this one extra electron, because if he does that, he achieves stability, he achieves happiness. And why is it so perfect? Because chlorine is only one away from getting that stability, that happiness. So they are a match made in heaven. Why is this called an ionic compound, though? When sodium literally transfers that electron over to chlorine, it loses an electron, therefore becoming a positive charge. And when chlorine accepts that electron, it has one more electron than it normally does, therefore it becomes a negative charge. However, if the sodium has a +1 charge and the chlorine has a -1 charge, what's the overall charge of the compound? Now, I'm not a mathematician, but 1 minus 1 does in fact equal 0. Goose egg. And that's how all of these ionic compounds are going to work. Once they have bonded together, they will always have an overall charge of 0. They are neutral. The individual atoms themselves may be charged, but the overall charge of the compound will be 0. Now let's get a little weirder. Let's say that this is not a bond between sodium and Claretta or sodium and chlorine. Let's say that magnesium is coming to the picture. Sodium is long gone. Magnesium. Let's take a look at what this might seem like.
So we just saw a visual representation of the bond between sodium and chlorine, but in chemistry, things aren't always as straightforward as they possibly could be. So now let's see if things get a little more complicated. Let's look at the romance between magnesium and chlorine. All right, shall we? So if you look at their placements on the periodic table, chlorine is going to look just as it did before, with its 7 valence electrons. Chlorine is only missing that 1 electron in order to be happy. Magnesium, however, is in family 2A, the alkaline earth metals, which means it has 2 valence electrons. So magnesium wants to get rid of 2 electrons. Magnesium starts a romance with Chloretta, and things are going great. And in the end, magnesium goes, listen, you're great. What we have is amazing, and I'd love to get something off my chest. Just as sodium did for chlorine, magnesium does the same. However, it's a different outcome. And magnesium says, you're awesome. You're almost everything I need. But you're not enough. So I have to ask you a question that would make most uncomfortable. But do you by any chance have a twin sister? And Chloretta says, oh my goodness. I never thought I'd be put in a situation like this, but I do. And her name is Chlorette. I know, it's very reminiscent of Chloretta, but here we are. What a crazy world we live in. And Chlorette is in the exact same situation where she is missing one electron in order to achieve stability. So magnesium needs 2 chlorines to make him happy. This got a lot more complicated. This is not a conventional romance, oh my goodness. But what would the chemical formula be here? Well, we're always going to write the metals first in these chemical formulas. There's only 1 magnesium and there's 2 chlorines, so the formula would be written as such. But we can get even more complicated beyond that. So let's say instead of a romance between magnesium and chlorine, let's say this is a romance between aluminum and sulfur. Oh my goodness, bear with me. We're about to get into a true 2020 romance here. Looking at aluminum's placement on the periodic table, it has 3 valence electrons, and sulfur has 6 valence electrons. My goodness, why was that hard to get out of my mouth? I'm not sure. But either way, looks kind of like so. So sulfur needs to gain 2 in order to be happy. Well, they spark a romance, and aluminum has the electrons in order to give 2. However, aluminum's not fulfilled. Look, he wants to get rid of this one. So, do you have a twin sister? She does. Her name is Sally. Here we go. In the exact same situation. And oh my goodness, aluminum is there to provide the electron. But Sally says, Al, you're not enough. Do you have a twin brother? He does. His name is Alabaster. And he's got the exact same situation going on as Al. But now Alabaster says, I'm not fulfilled in this. I'm not going to start this relationship unless I'm feeling fulfilled. So I'm going to go out on a limb here. Are you guys triplets? They are. They are indeed. Oh my goodness. This story just gets crazier and crazier and crazier. But look, now it's a perfect setup. The sulfurs have all gained 2 electrons, and both of my aluminums have given up 3 electrons. A match made in heaven. What would this chemical formula be? Well, I've got 2 aluminums, and I've got 3 sulfurs, so it'd be written as such. If only I didn't have to draw this every time elements got together to engage in romantic partnerships. If only there was a shortcut.
So we've just drawn a couple more compounds, one with magnesium and chlorine, another one with aluminum and sulfur, and you're getting a little worried. You're saying, do I really have to draw this all the time to figure out what their formulas are going to be to make them happy? If only there was a more simple way. And there is, ladies and gentlemen. It's called the crisscross, the swap and drop, the flip-flop. Whatever floats your boat. I'm personally a crisscross kind of guy, but that's just because I love the 90s hip-hop group Crisscross, spelled with 2 Ks. Love that track. I really do. Add it to your playlist. Culture yourself, ladies and gentlemen. But what it really is you simply take the charges that you've labeled at the top of your periodic table for the elements associated in this compound that you're drawing, and all you got to do is flip-flop them. Crisscross them, make an X with the charges. The 2 from the barium goes to the chlorine, and the 1 from the chlorine goes to the barium. So I need 1 barium and 2 chlorines to make this group happy. Because listen, in the end, if these elements on an individual basis aren't going to be happy at the end, then they're not going to get together. That's the whole bottom line. And remember, the overall charge of these compounds must be 0 at the end. Okay? So it really is as simple. We drew it all crazy like on the board, but in the end, what do we find? It would take 2 aluminums and 3 sulfurs. Well, all you got to do is flip-flop those charges. You might be asking, where are the negatives? Where are the positives? They're still there. They are still there. Remember, the atoms themselves can be negatively or positively charged, right? But what does it mean to have a negative amount of sulfur atoms? That's not possible. So this is the amount of the atoms, but the charges are still there. So 2 times the plus 3 charge of aluminum is positive 6, and 3 sulfurs times the negative 2 from the sulfurs is negative 6. 6 minus 6 is 0. The charges are still there, but you can't have a negative amount of atoms. Never, 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 never should you have a negative number written in a chemical formula. Do not do that. You'll never see it anywhere, okay? So now, let's do a few more examples. Rubidium with sulfur, barium and phosphorus, magnesium, and oxygen. Here we go.
I apologize for the slight change in camera format, but I have found myself without a dry erase marker. Oh my goodness. So let's do these 3 examples of ionic compounds, and we're going to show you the shortcut method with them. And so we've written out the element symbols of the elements that were just on the slides that are depicting the examples that we're doing here. And all we have to do is we have to track them down on the periodic table to see what charge is associated with that element. What is going to make them happy? Well, rubidium is an alkali metal, therefore he is going to lose 1 electron, a positive 1 charge. Sulfur would like to gain 2 electrons. And you know what? Let's just go ahead and go down the line here. Barium is an alkaline earth metal, wants to lose 2 electrons. Phosphorus wants to gain 3 electrons. Magnesium wants to gain 2. And oxygen wants to gain 2. So where are we getting these numbers? Remember, we're looking at the periodic table. We labeled our periodic table towards the beginning of this video, and we are looking at what is going to make these elements happy. And then all we have to do is crisscross. So the formula that's going to be formed between rubidium and sulfur is it's going to take 1 sulfur and 2 rubidiums in order to make this a balanced formula, like so, Rb2s. Ba2 is going to, or the 2 is going to cross over to the phosphorus, the 3 is going to cross over to the barium, and so this is going to be Ba3P2, like so. And then magnesium and oxygen, think about this mathematically. If magnesium wants to lose 2 electrons and oxygen wants to gain 2 electrons, do I actually need 2 of each in order for them to make each other happy? And the answer is no, I don't. Not at all. I actually only need 1 of each. Therefore, whenever they crisscross, yes, it's at first going to look like this, but just like in math class, you would get points off if you didn't reduce your fraction. We can reduce this as well. And so we're going to get MgO, because I actually only need 1 of each in order for them to be happy. And those are our examples.
So we have one last thing to cover before we actually get into naming these compounds, and that is sometimes there are groups of elements that stick together. They're happy together, and these are known as polyatomic ions. Break those words down. Poly meaning multiple, atomic meaning atom, ions meaning charged. So it is a group, multiple atoms together that have a charge. Can be positive or negative. But I call these guys the chemistry gangs of the periodic table. The Bloods and the Crips of chemistry. And they never get separated, and they never change their look. Listen, they've established their reputation. They've worked hard. They've done some terrible things in their past. And maybe they're meant to be judged for that. Maybe they're not. I don't know, okay? But this is who they are. And they're not going to change their formula. They're not going to change their makeup. Now, their numbers might go up and down. They might add more of the group, but they're never going to change what they look like. Okay? So, never, ever, ever change the formula of the gang. Now, what I'm going to do is I'm going to link the sheet that I use in my class below this YouTube video as well, so feel free to utilize that. But there's lots of polyatomic ion sheets. Maybe your school uses more, maybe your school uses less. But there's a lot of polyatomic ions out there, okay? And it doesn't hurt to have more at your disposal. But they work the exact same way as an element. But the key, the critical component here is that you do not change what they look like. They have a specific formula. They have a specific charge. You don't get to change that, and it doesn't matter what they're attaching to, all right? They behave just like elements. It's just that there's more than one element there. So let's do these examples on the board: sodium and sulfate, magnesium phosphate, ammonium and nitrogen, calcium and carbonate.
So now we're going to break down how to write these ionic compound examples using those polyatomic ions. So what you want to have handy with you is your periodic table, of course, along with your list of polyatomic ions. Whichever one you're using, what we're talking about right now are the most common ones that you're probably going to see throughout this course. So our first example is sodium and sulfate. Sodium, just being an element, a metal, all we got to do is look at where he is on the periodic table. He's going to have a positive 1 charge. Sulfate is a chemistry gang with the formula SO4 with a charge of -2. I am never going to change this SO4, okay? But how this polyatomic ion works is it behaves just like an ordinary element. We are going to crisscross their charges, and so now this 1 is going to go to the sulfate, and this 2 is going to go to the sodium. So for the formula between sodium and sulfate, I just get Na2SO4. The second example is between magnesium and phosphate. Magnesium has a charge of 2. Phosphate, if you look at your polyatomic ion sheet, is PO4 with a charge of -3. Exact same technique. Crisscross, swap and drop, whatever floats your boat. This 3 from phosphate is going to go to magnesium, and this 2 from magnesium is going to go to phosphate. I am not going to change the PO4. A lot of you, I'm going to write it incorrectly here, a lot of you would try to do this. And what you're doing here is logical. I don't blame you. You're multiplying everything within PO4 by 2, but that is changing the gang. Now it's not phosphate. Phosphate is PO4 with a charge of -3. That's not phosphate. That's something else, a totally different beast. So instead, what we're going to do is we are going to put the gang in parentheses so that we don't change its formula. However, what these parentheses are going to allow us to do is increase how many gangs there are. So we're going to put the PO4 in parentheses, and there's 2 of them, like so. All right, and we've got a couple more examples. The next one is between ammonium and nitrogen. Ammonium, I believe, is the only positively charged polyatomic ion that we talk about in our course. So here we are. It has a positive 1 charge. Nitrogen has a -3 charge. We're going to utilize what we just did in the previous example right here. Never change the gang. So we're going to crisscross. We're going to slap the ammonium in parentheses, like so. NH4,3N. If you don't have the parentheses, it is not correct. Then we're going to look at calcium and carbonate. Calcium has a charge of 2. And once again, if you're wondering where these charges are coming from, these are just the elements. So what you need to be looking at is that periodic table that hopefully you put those charges at the top of the families, as I told you to do at the very beginning of this video. If you didn't, go look back at the beginning section. Notice that both of these have a charge of 2. So if I went about my business just normal, it would end up looking like this. But this is incorrect. This is just like in math if you left a fraction 2/2. Or let's say it's a different example. Let's say you left a fraction 3/6. I don't know how much education has changed since I was in high school, graduated in 2013, but all I know is if I didn't reduce a fraction, I got points off. And it kind of works the same way in chemistry in that, well, if calcium wants to lose 2 electrons and carbonate wants to gain 2 electrons, why do we need 2 of each in order for them to be happy? We don't. Because economically, we only need 1 of each to make this transaction happen. So think of it like reducing your fraction. And so if you left it like this, I would count it wrong. But what you should do is get rid of these 2's, and you can write it as so. And now that you've reduced it, you actually don't even need the parentheses. So it should just be CaCO3. And let me condense it even more, so it doesn't look like there's a space in there. And there we go, calcium and carbonate.
So now that we have all the possible components that are getting involved in these ionic compounds, now we can name them. And here's how it works, and you've probably seen this before, but let's take our first example that we wrote out here today, which is NaCl. And you've probably heard the name of that before, aside from just being table salt. The chemical formula name is sodium chloride. Sodium chloride. Notice that the metal did not change, but the nonmetal did. And so the way that I think about this is I always think about these ionic compounds as a marriage, okay? And we explained that in great detail on how the metal is proposing to the nonmetal. So, traditionally, right, if we're talking about just a traditional marriage, the metal is a male and the nonmetal is a female, okay? So, does the male typically change his last name? Not traditionally. Now everything goes, right? And of course there's situations for that, but traditionally no. And traditionally the nonmetal, the lady, does change her last name once they get married, okay? So I always think of it that way. So in this ionic compound between a metal and a nonmetal, not a polyatomic ion, the metal never changes their name and the nonmetal changes their last name to IDE. Doesn't take too much practice there because it's whatever the root of the element is, then IDE. That's it. Okay? Here's the kicker. If you are working with a polyatomic ion, a chemistry gang, remember the gang has worked hard to establish its reputation, why would it change its name? When something called nitrate strikes an image into your brain, it's not going to change its name. It worked hard to make that a powerful name. And so, it's very simple. When it's a metal with a polyatomic ion, you don't have to do anything. You just have to know the name of the metal and the name of the polyatomic ion. Okay? And look at this bottom example. Two polyatomic ions getting together. I don't have to do squat. All I gotta do is look at my polyatomic ion list, slap those names together. It's cake. It's simple. So let's name a few examples. All right. CaBr2, CS3N. All these. This is cake. All I got to know is I sure hope that I practice my elements' names, and then I've got my polyatomic ion list that's got all of those on there as well. So if you see a chemistry gang, take a look at your list. If you see just an element as the nonmetal portion or the negative ion portion, well then you're going to have to change the last name to IDE. So Ca, calcium, Br is bromine, so this is a nonmetal and not a gang, so I'm going to have to change the last name here. Cesium, nitrogen is not a gang, it's an element, so I'm going to have to change the last name to IDE. Sr is strontium. SO4 is sulfate. This is very obviously a chemical gang. Now, these parentheses aren't actually required here because the subscripts reduced down to 1 because they were the same charge, but I put them there for extra emphasis. But either way, SO4 is a gang, and that's sulfate, so we don't have to change the last name there at all. Rubidium with sulfur. Sulfur does have to change its last name. And then magnesium with a gang. This is known as hydroxide, which is always OH. There are no H's in chemistry, ladies and gentlemen. There are only O's in chemistry. And so this is OH, not HO. And this has a -1 charge if you're looking at that, but it has a name of hydroxide. And then sodium is getting with another gang called chlorate. Once again, these parentheses are not required, but we put it there for extra emphasis. So take a few seconds, right? Feel free to pause this video right now because we're going to show you the answers here in a second. Take a few seconds. Try to write down in your notes or wherever you're writing what you think these names would be. And then 3, 2, 1, voila, here they are. Notice, anytime it's a metal attached to a nonmetal, the nonmetal's last name changes to IDE. Anytime a metal is attached to a chemistry gang or a polyatomic ion, the name does not change. Okay? Takes a little bit of practice, but all in all, not so bad, right? Not so bad. So let's look at our last type of ionic compound, and this is with those elements that we avoided in the beginning. Remember, we skipped over the transition metals, the B block elements. Well, now they are here. And the reason why we skipped over them is because they're kind of crazy. They're a little loopy. And I like to think of this as them having multiple personalities. Because how it works, with the elements that we labeled in the beginning, we only put one charge at the top because they act very consistently. However, the transition metals can be happy in a variety of ways. And so, look at all these. Some of them are especially crazy. You thought Nicki Minaj was crazy with her 3 personalities? Look at manganese, 5 personalities. Technetium, 6 personalities. Ruthenium, 7 personalities. Oh my goodness. You can think of this as a blessing or a curse because they're happy with just about anything, but also unpredictable. You have no idea what they're gonna hit you with on any given day. So now, here are the rules with this. How we name these compounds that involve the transition metals, we have to indicate which personality of the metal we're dealing with. And the way that we do that is with a Roman numeral. We do it with a Roman numeral. So any transition metal, you have to have a Roman numeral in the name, with a few exceptions. And those exceptions, I know there's more than just these three on this sheet right here, but the three exceptions that I would encourage you to mark down in your periodic table right now are silver, zinc, and cadmium. Silver, zinc, and cadmium only have one possible oxidation state. Silver always has a charge of 1. Zinc and cadmium always have a charge of 2. And now that I'm looking at this actual picture here, I know for a fact nickel can have more than one oxidation state. Scandium can have more than one oxidation state. So this might not be the most accurate oxidation state list. You don't have to memorize the oxidation state list. That's what I'm trying to get across to you, is you're always going to be able to figure it out. However, silver, zinc, and cadmium do not need Roman numerals, but there are a couple of exceptions outside of the transition metals that you want to point out to yourself as well, because they can also have multiple personalities. And one of those is lead. Lead is not a transition metal. He's located in the carbon family of the periodic table, yet he can have multiple personalities. Also, tin. I would put little stars next to tin and lead on your periodic table because they both can have oxidation states or charges of +2 or +4. And so, when I'm looking at this name right here, lead-2 iodide, lead-4 iodide, this is simply telling me the charge of the metal. Anytime you see the Roman numerals written, it is telling you the charge of the metal. It is not telling you how many of that metal there are. It is telling you the charge. So what do you have to do with that? You have to crisscross it in order to get the correct formula. So that's pretty simple. So lead-2 iodide would be PbI2, and then lead-4 iodide would be PbI4 because iodine only has a charge of -1. So that's pretty simple. However, if we're going backwards, if we are naming compounds that are going to require Roman numerals, it might be a little more tricky. So we're going to solve these on the board. Keep in mind, remember these first couple examples with tin. Remember, tin is outside the transition metals, but still needs a Roman numeral. All right, so let's do these examples on the board and give you a little sneak peek on how I approach them.
So now let's assess how we are going to name these ionic compounds that are utilizing transition metals. So we're going to have Roman numerals involved. Remember that the Roman numeral specifies the charge of the cation, the charge of the transition metal, not how many there are. So we have 5 examples in front of us. We've got 2 involving tin, we've got 1 involving tungsten, and 2 involving copper. All right? Let's start off with the tungsten one. So this is actually the third one in your notes, and the formula is W2O3. This example is really how most of them end up being, but some of them are a little bit trickier, and that's what we're going to dive into here in a second. But anyways, what you have to kind of do is undo the crisscross. And this is a very logical process for a lot of us, but some of us, we get kind of stuck with it, and so we got to see it done in front of us. And so remember how we got here. This is the final product. And what occurred here is the charges were swapped and dropped in order to make everyone happy. So what we're going to do, since the Roman numeral is the charge of our tungsten here, tungsten is our unknown, and so I'm going to put a question mark here, but oxygen always has a charge of -2 in these compounds. So when they crisscross, this is the result when they crisscross, and this makes a lot of sense because if oxygen crisscrossed a 2, that's what I expect to see there. So if tungsten crisscrossed, what charge did he start with originally? And that is that +3 charge. So this name of this compound is tungsten 3 oxide. A lot of people, and if this was a multiple choice test, I guarantee one of the choices would be tungsten 2 oxide. Why would they do that in order to trip you up? It's because of this 2 right here. A lot of kids mess it up and say that the Roman numeral is how many of that metal atom that there is. Okay? So there it is. And this is how most of them end up. They end up being very, very simple, where pretty much all you have to do is look at the subscript of the nonmetal that it's attached to. However, sometimes there are little hiccups with this. So let's take a look at our first two examples then that are involving the element tin. So we've got SnSO3 and SnSO3-2. Like so. Okay? There is going to be a difference in their names, and that's because this is not the same chemical. And that's why we need those Roman numerals. If I just said tin sulfite, well, which one? And remember, tin is not technically a transition metal, but sort of behaves like one. It does have two different oxidation states, two different charges, and so we're going to figure out which one of those are, or which one of these each of them are. There's only two different possible ones for tin, and so we're going to assign those now. And so what we have to do is undo the crisscross. Tin has a mystery charge, but sulfite always has a charge of 2. Excuse me. Always has a charge of 2. And so, when they crisscross, what should I expect to see as a subscript for tin? I should expect to see a 2. However, I don't see anything. And what does it mean when I don't see anything? What number is technically there? A 1. Which means this number was reduced. Oh my goodness. So what you should be thinking in your head now is, oh my goodness, tin either has the same charge or a multiple of that charge that was able to reduce with the number 2. So now what I got to do is, what is the subscript next to sulfite in the formula? Well, there's nothing there, which means it's a 1. And if both of these numbers reduce to 1, then that means both of them were the same charge to begin with. Ludicrous! So this is not just tin sulfite. This is tin 2 sulfite. Boom! Like so. Not so bad, easy peasy. So let's do the same thing for the bottom one. We know that they crisscrossed. And sulfite always has a charge of 2. So when they crisscross, if everything goes normal, I should expect to see a 2 right here. But I don't. I once again see a 1. Well, that means that this charge was divided by 2. Oh my goodness. So what charge would tin have to have if it crisscrossed over to the sulfite and had to also have been divided by 2 to become a 2? What divided by 2 equals 2? 4. Oh my goodness. So this is tin 4. Kind of sounds like trucker talk. Tin 4, good buddy. So let's look at the last two examples with copper. All right, we have Cu2O and CuO. Copper has two different oxidation states, so let's figure out which one is which. Well, when they crisscross, positive, oxygen always has a charge of 2. So, when they finish their crisscross, what number should I expect to see next to the copper? I should expect to see a 2. And in the top example, that's exactly what we see, which means nothing actually changed here, nothing was reduced here, so this copper had to have had a charge of just 1. So this one is copper 1 oxide. However, in this formula, I don't see a 2. In fact, both of the elements in the formula have a subscript of 1, which means they were both reduced by 2. So if oxygen had a charge of 2 and became 1, then copper also had to have a charge of 2. So copper 2 oxide. So most of the time it's simple like our first example. Other times you have to undo the crisscross to make sure any reducing shenanigans didn't go on. And if they did, get to the bottom of it. Move on.
Here we are on the other side of ionic compounds, which, as we said in the beginning of the video, far and away the longest amount of time required to learn. Here we are with covalent compounds, which is going to take a grand total of maybe 5 minutes of your time. So bear with me, because you've actually been naming covalent compounds all of your life, whether you knew it or not. Pretty awesome. So we actually referenced the term ionic and covalent actually way back in Unit 2 and Unit 1 when we were discussing properties of matter and all that. Whenever we were discussing the differences between an ionic compound and a molecule. Okay? So now we get to actually decipher what a covalent bond is. Well, it is a bond between two nonmetals. And if you look up what the word covalent means online, it's something along the lines of sharing, because that's exactly what's happening in a covalent bond. In an ionic bond, it's a metal donating electrons to the nonmetal, because that tickles both their fancies. That's what both of those elements want. One wants to give, one wants to take. But now, with two nonmetals, neither is willing to give up electrons because they both want to gain electrons in order to reach their stable valence octet that they're going for. So these guys, what they're going to do, instead of roughing each other up in the dark alleyways and stealing the electrons from each other, they go about it peacefully. And they go, you know what? You need two, I need two. Let's just hold hands, man. Let's do this together. Let's reach nirvana together. And so that's what they do. They share electrons. So there is no exchanging, which means there are no positive and negative charges. There are no ions to worry about. Sharing electrons does not mean transferring electrons. So let's take a look at the rules here. There's only a couple rules. First word, prefix is going to indicate the number of atoms only if there is more than one atom. Second word, you are always going to have a prefix for the number of atoms plus the root name of the element, and you're always going to end in IDE. So aside from the prefixes, this is no different than the ionic compounds. We're always going to end in IDE. Now, let's do an example that is going to sound incredibly familiar. It should sound incredibly familiar to you. Carbon dioxide. What's the formula for carbon dioxide? Well, there's no prefix in front of the carbon, so how many carbons do you think are there? One. You guessed it. Carbon. Dioxide. What's a di? Well, you don't call it a dicycle, you call it a bicycle. Yet, the two prefixes mean the same thing. Di means two. So the formula for carbon dioxide is CO2. The prefixes are telling you how many of each element there are. But notice, we did not say monocarbon dioxide. If there was more than one carbon, you would have to have a prefix. But if the first element, there's only one atom of that element, you are not going to have a prefix. And that's just to condense things down. That's to save ourselves some syllables, okay? But there is no crisscrossing of charges because there is no transfer of electrons. So all you got to do is pay attention to the subscripts or pay attention to the name, depending on what direction you're going for. So let's name these together. Let's name these together. We already did CO2, carbon dioxide. Now let's look at CO. You've probably heard it before. There's only one atom of the first element, so it's still just going to be carbon. We're not going to say monocarbon. However, the second element always gets a prefix. So this is not carbon oxide. This is carbon monoxide. Or, if you want to condense it down, carbon monoxide, which is that gas that is vented from your car out of your exhaust pipes out the back. Okay? Right here we have the chemical formula for a pair of cheeks, as you can see right here. But there's two arsenics, so this is going to be diarsenic, and there are 5 sulfurs, so it's pentasulfide. The hardest thing about this is you got to know your prefixes. And because a lot of you have probably already taken geometry or you've at least referenced geometric shapes in the past, you probably already know most of these prefixes. In fact, the only ones that you might be a little unfamiliar with are tetra. Instead of saying quadrilateral, we would say tetralateral if you were a chemist in the geometry world. And then maybe hepta. 7, for whatever reason, it's just not too frequently used in geometry. I know you've probably heard of a heptagon, but if you haven't, that's what it means. It means a polygon with 7 sides. Hepta is 7. But tetra and hepta, that's really all you got to look at that's going to shake you up. Okay? So next example, We've got 2 chlorines, therefore that is dichlorine, and 7 heptoxide. You could also say heptaoxide. You can also just save yourself a syllable by condensing that A and that O. Right here, this is a very famous gas. You might have heard of this one. This is sulfur, because there's only one of them. Sulfur hexafluoride. And this is what does the opposite of helium. You can breathe it in, actually. Helium makes your voice go really high. Sulfur hexafluoride makes your voice go really, really low, because it's a very big gas. If you were to add up all the masses on the periodic table, you would see that it is much heavier than helium. Therefore, it is more dense than the air that is in your lungs, and therefore makes your voice go low. That wasn't voice effects. That was me totally natural, just talking really deeply. Was that convincing? I don't know. We'll have to play it back. Anyways, then we've got phosphorus bonding with oxygen. There are 2 phosphoruses, so it is diphosphorus, and there are 5 oxygens, so it is pentoxide. Diphosphorus pentoxide. Not so bad, right? So here we are with our answers as we just discussed. Just notice a couple things here. First of all, notice we don't capitalize the elements whenever they're starting a little bit later in the name. Diarsenic, for example, we don't capitalize that A. I've seen a lot of people do it. It's not technically correct. On top of that, we are also condensing some syllables here. We are saving ourselves some vowels. Instead of saying monoxide and having 2 O's here, we condense it down to 1. Instead of saying heptaoxide and having this A right here, let's go ahead and look at what that would be like. Heptaoxide. A lot of kids are going to want to do that from the get-go. Totally understandable, but you can save yourself a syllable. Heptoxide. Rolls right off the tongue. Same thing we did with pentoxide right here. So, all in all, covalent, super, super, super simple. And it's so simple that a lot of kids want to put these prefixes on everything. Right? Sodium monochloride. Manganese 5 pentachloride. Man. It sounds so easy to just look at the number of how many there are and slap a prefix on the front of it. It seems very appealing, very juicy. But that's just not how the cookie crumbles, ladies and gentlemen. You've got to come to grips with yourself. You've got to look yourself in the mirror and say, listen, buddy, the easy road is not always the right road. There's a time and a place for prefixes. And it is not with ionic compounds, ladies and gentlemen. Say it with me. I will not put prefixes on ionic compounds. Very good. Well done. Here's the deal. An ionic compound is between a metal and a non-metal. If you see a metal, I should never have prefixes. A covalent compound is between 2 non-metals. You have to be able to assess what types of elements you're dealing with whenever you see a compound. All right? So that's really the hardest thing about this, is knowing when and when not to use these prefixes. Now let's go the other way. Let's go to writing the formulas from the following names. And you know what? We're going to let you try this on your own. Okay? We're going to flash the answers here in a second. Okay? So feel free to pause right now. All right, so let's take a look at your answers here. If you got the right answers, awesome. If you didn't, let's discuss why that might have been the case. Starting off with carbon tetrachloride. I would say the biggest thing that you probably would have did if you got it wrong would be C4Cl. And what did you do there? Well, you took the prefixes that were given to you. You got those numbers right, but then what'd you do? You crisscrossed them. So you said the 4 is associated with the chlorine, but you crisscrossed it over to the carbon. You treated it like an ionic compound in which electrons are being transferred. Remember, in a covalent compound, that is not occurring. They're just essentially holding hands, okay? Everyone's holding hands. It's super happy. It's a beautiful moment, okay? Dinitrogen octoxide. These prefixes are straight up telling you how many of each element there are. The di goes with the nitrogen. The octo goes with the oxygen. So there's 2 nitrogens, 8 oxygens. If you got it wrong, you probably did N8O2. That would probably be the number 1 most missed way of doing this. Another thing you could have done is you could have taken their charges in association with the periodic table and maybe did N2O3, that sort of thing. But that would never happen, and that's for different reasons that we can expound upon a little bit later. Triphosphorus decasulfide. So this is a real big, thick with 3 C's molecule here. Triphosphorus, 3 phosphoruses, and deca is the prefix for 10. So 10 sulfurs. No surprises there. And then nitrogen monoxide, the chemical formula for no. The chemical formula for yes, it's just not here. It's a shame. So, nitrogen monoxide, here we are. No surprises. We did not say mononitrogen monoxide. We simply said nitrogen monoxide. Congratulations. You've made it through covalence. I would say a whole heck of a lot easier than ionic compounds. Hardest thing, just do not slap those prefixes on every compound when you face them. All right, so now let's take a look at acids. Okay, acids are this really cool in-between world between ionics and covalent compounds. It is a covalent compound where hydrogen is bonded to a nonmetal or a chemistry gang, a polyatomic ion. And hydrogen is super special. If you look at where he's located on the periodic table, he's in the very top left. He is a nonmetal, but he behaves like a metal. What a spicy element. He is a nonmetal, but behaves like a metal. And what that means in this case is he is very happy to give up an electron, which means these nonmetals are happy when hydrogen comes along because they can pluck the electrons right off of him. It's beautiful, beautiful transaction. Hydrogen's happy to lose an electron. The nonmetals and the chemistry gangs want the electrons. So, here they go. So, it is a covalent compound in which electrons are being shared. However, electron transfer can take place. Therefore, crisscross, crisscross, we have to crisscross here. That being said, this is much easier to crisscross because hydrogen's charge is always +1. So, what that means is whatever the charge of the negative ion, that's how many hydrogens you're going to need here. So it's very easy to identify acids because all acids start with the same element, hydrogen. And there's two categories we're going to talk about. We're going to break it down into two categories. And the first category is binary acids, an acid with only two elements. And we know that an acid has to have hydrogen. Therefore, hydrogen is one of the elements, and the other element is just whatever nonmetal it's attaching to. And so this has a very special way to name it, and this is where a lot of kids go wrong. Okay, this special way to name it is they always start with the prefix hydro, then it's whatever the root of the nonmetal is that it's attaching to, followed by the suffix ic. Okay, so HCl, which is probably one of the most common acids you could have possibly heard of before starting chemistry, hydrochloric acid. How do I know this is a binary acid? We'll take a look at its formula. It's only two elements, hydrogen and chlorine. Now, what a lot of kids do is they take every acid and slap hydro on the front of it. That's the number one mistake kids make with acids, okay? But it only applies to binary acids. It only applies to binary acids. So, it's very simple for all the rest of these. It's the exact same setup, exact same template. And it doesn't matter that there's more hydrogens here. It doesn't matter that there's 3 hydrogens in this example, because this isn't a covalent compound. I'm not going to have to put prefixes here. The fact that it's an acid, I know how many hydrogens are going to be there, and it's based off of the charge that the nonmetal is that the hydrogen is attaching to. So HBr, it's a binary acid. It's only 2 elements, hydrogen and bromine. This is hydrobromic acid. H2S, I'm going to say it a couple different ways here, okay? Why is it H2S? Well, if we look back at the periodic table and how we labeled it, sulfur wants to gain 2 electrons, therefore this should have a -2 charge above the periodic table. At least that's what we were doing towards the beginning of this video. So I certainly hope that you have that ready at your disposal. Hence why it crisscrossed and formed H2S. So a lot of you might want to say hydrosulfic acid, and I don't blame you. I think that's right. But for whatever reason, chemists who created this naming system well before you or I were born or thoughts in our parents' heads, they said, you know what? When it comes to acids, I think sulfur and phosphorus should have an extra syllable. I just think it should. I don't know. It's just kind of wacky. Just kind of quirky. I've just got the crazy energy. So it's not hydrosulfic acid, although if I were your teacher, I'd be counting that right if you wrote that down on your page personally. It's hydrosulfuric acid. Hydrosulfuric acid. And we'll flash the answers here in a second so you can see how that's spelled and all that. And then H3P, why is it 3 hydrogens? Well, it's because the charge of phosphorus that we labeled back on the periodic table towards the beginning of this video, phosphorus wants to gain 3 electrons. So how many hydrogens is it going to need in order to be happy? It's going to need 3. Therefore, H3P. And as I just said, it doesn't only apply to sulfur, because a lot of you might want to say hydrophosphoric acid. I don't blame you. It's actually hydrophosphoric acid. Okay? And then HF, this is just simple like the first couple that we did, hydrofluoric acid. So let's flash these answers up here for you. All right, and there they are. We can see how they're spelled. Notice how sulfur is actually using its full element name as opposed to just sulf. Kind of weird. Like I said, counterintuitive to what I would believe as well. And phosphorus has that extra syllable as well. That being said, if you were looking at a multiple choice assessment, I would think your teacher's pretty cruel if they give hydrosulfic and hydrosulfuric as an answer choices, as two different answer choices, I mean. That's really mean in my opinion, so I doubt it would occur. Or hydrophosphic and versus hydrophosphoric right here. That'd be really mean. And so if any teachers are after, come on, be a little nice. So now let's look at it when it's not binary acids, okay? And I think that these are really easy to name. Once again, hydro only applies to binary acids. Well, this other category we're dealing with are called tertiary acids, an acid with more than two elements. And what it typically is hydrogen attached to your polyatomic ions. And we're going to talk about how these polyatomic ions get their names here at the very tail end of this video, which is very, very important because there are hundreds of polyatomic ions out there. You're probably only going to use a few dozen in your chemistry course, but there's tons out there, and you should know how that they are named. And that's also going to benefit you when you're naming the compounds that they form with those polyatomic ions following that. So anyways, how do we name these polyatomic ion acids, these tertiary acids? Well, there's a very easy mnemonic device. If the polyatomic ion or the chemistry gang ends in -ate, the suffix of the acid becomes -ic. If the polyatomic ion ends in -ite, the suffix of the acid becomes -us. So here's what I do. Here's what I say in my head. I ate something icky, so I drank Sprite, and it was delicious. Oh my goodness, how can you miss any question with that? So here's the deal. All you got to do whenever you're naming these is all you got to do is look at the gang that the hydrogen's attached to. You know that the hydrogen's going to be there, right? It's an acid. All acids have hydrogen. So all I care about is this SO4 right here. And yes, it has a charge of 2. That's why there's 2 hydrogens there. So all I got to do is I got to look at my chemistry gang polyatomic ion chart. You're going to need those for this very last part of the video. I got to look at what SO4 with a charge of -2 is. Turns out his name is sulfate. It ends in -ate. Therefore, the ending of the acid becomes -ic. And remember, scientists, for whatever reason, thought sulfur should have its full name whenever we're talking about acids. So instead of sulfic acid, it's sulfuric acid. Then if I look at H2SO3, all I care about is the SO3 with a charge of -2. I look at my chemistry gang chart. I find it. His name is sulfite. Oh my goodness. Sulfite. So therefore, the ending of the acid becomes -us. Sulfurous acid. So try to tackle these over here. We're going to actually solve these on the board because I like to walk you through my logic on this one. So feel free to pause it right here and try to tackle it as best you can. You're going to need your polyatomic ion sheet. If not, if you don't, feel free to Google polyatomic ions on your devices. Okay?
Let's practice naming these tertiary acids. I have already written the first 3 examples that are in your notes, and this is where we are going from the formula to the name. Now keep in mind, every acid always starts with hydrogen. Could be one, could be multiple hydrogens. It doesn't matter. The amount of hydrogens doesn't actually matter for the name, because with these tertiary acids, all I care about is the polyatomic ion that they're attached to. And so if you have your polyatomic ion sheet handy, which you should for all of this video, all you got to do is look for something that looks like ClO3, NO2, and MnO4. And remember that mnemonic device. I ate something icky, so I drank Sprite, and it was delicious. You know, to quell the tummy, okay? So all you got to do is remember that. And so what I'm looking at for on my polyatomic ion sheet is ClO3, and I find that that is chlor-8. And if this polyatomic ion ends in -ate, then that means that this acid will become, or will have the ending -ic. So this becomes chloric acid. Not hydrochloric acid. We just learned about binary acids on the previous set of slides. Hydrochloric acid had a different chemical formula. for very good reason. When I say hydrochloric acid, I don't want scientists to think two different formulas. I want them to think of one formula and one formula alone. They behave very differently. So let's look at HNO2. NO2, its polyatomic ion is nitrite, which ends in ITE. Remember the mnemonic device. I drank Sprite because it was delicious. So ite to us. So it becomes nitrous acid, like so. And then the last one, MnO4, its gang name is permanganate. All you gotta do is substitute that 8 for ic, and you're good to go. Do not put hydro on these. So this one becomes permanganic acid. Now let's take our tertiary acids and go the other direction. Let's go from the formula, or sorry, from the name to the formula. And as long as it doesn't start with hydro, you know that it's a hydrogen attached to a gang. Therefore, the only thing you care about are the suffixes of these acids. If it ends in us, then I know what the ending of the gang is going to be, and if it ends with ic, then I know what the ending of the gang is going to be. So, this doesn't start with hydro, it starts with hypo, so it's very easy to mix that up, but hypo and hydro, very, very different. Hypochlorous means that the gang that hydrogen is attached to starts with hypochlor and ends with ite. And if you're looking at your polyatomic ion chart, then hypochlorite is just ClO with a charge of -1. Because they both have charges of 1, this formula is going to be very, very simple. All we got to do is crisscross, and it simply becomes HClO. Phosphoric acid, that means I'm looking for a polyatomic ion that starts with phos and ends with 8. You might be looking for phosphorate, but hopefully you wouldn't see that there, and see that the only option there is phosphate. Awesome. We know that it's going to be hydrogen crisscrossing with phosphate, which is PO4 with a charge of -3. We crisscross them to make sure we've got the proper amount of hydrogens. But remember, whatever the negative charge, whatever the negative ion is, that's how many hydrogens I'm going to need. So this one is just H3PO4. Then for our last one, bromus, because it ends in us, that tells you that the gang ends in ite. So I'm looking for bromite. And your polyatomic ion chart, the common ones don't actually have this one on there, but we're going to teach you a little trick here in the next minute of the video that's going to show you how to find out what that is. But some of you might have it on there. Bromite. We know that it's going to be bonding with hydrogen. Bromite is simply BrO2 with a charge of -1. And so we crisscross them, and we simply get HBrO2. Tertiary acids.
So as I said when we were first talking about the acids, is the very last part of this video is how to actually name these polyatomic ions. Because how it often is in the class is you're going to receive a list of polyatomic ions. However, that may or may not contain all of the polyatomic ions that you're going to need and utilize in your course. So what are you going to do if you see a polyatomic ion that you're unfamiliar with and your teacher hasn't told us what it is? Well, there are some tricks to this. All right, and there's a couple different tricks we're going to teach you. First one's going to be right here on your screen. The next one is going to be on the board here because there's a lot more we can extract from the ones that we already do know. And the first one are halogen polyatomic ions. Okay, most polyatomic ion sheets that I've ever come across have every variant of a chlorine polyatomic ion in there. And if you take a look at yours, it probably has chlorate, chlorite, hypochlorite, and perchlorate on there. Okay? Well, halogens, and this as far as I know only applies to the halogen family, but they're all in the same family. So we've got fluorine, we've got chlorine, we've got bromine, right? All of those guys in that family you can utilize this trick on. Okay? If chlorate is ClO3 with a charge of -1, then bromate is BrO3 with a charge of -1. And because they're all the same, electron configuration essentially, all you got to do is swap out those elements. And then, of course, swap out the root of the elements in the name, right? If chlorite is ClO2 minus, then fluorite is FO2 minus. So that's a little trick there. And so what they do on these polyatomic ion sheets is, in order to save ink, they don't write every variant of every halogen polyatomic ion. They usually just write the chlorine ones. Why they do the chlorine ones over the other halogen ones, I'm not sure. But they just do it in order to save ink. There is a relationship there. And so now, what I really want you to do is pay attention to those chlorine polyatomic ions, because we're going to use them as a baseline for the very last part of this video. Okay? So now, what I want you to do is look at these examples right here. HBRO, H2CO2, all of these down here at the bottom. I don't have these gangs anywhere on my polyatomic ion sheet. How am I going to tackle this? Well, what you are going to do is you're actually going to take your polyatomic ion sheet and extract different polyatomic ions that aren't explicitly written, but you can determine using the relationship that we are going to learn about right now. So the polyatomic ion suffix endings and the prefix attachments that they utilize are determined by how oxygenated the molecule is, how oxygenated the polyatomic ion is. Okay? And so I'm going to show you a little relationship on the board now, and then we're going to come back and we're going to tackle these examples on the bottom of the screen.
For the very last part of the video, I want to teach you a little trick on how to name these polyatomic ions. Because how it often is you're going to get a list, but that's not all the polyatomic ions of the world has to offer, and sometimes you have to use some of those that aren't on your list. Well, here's a little trick on how to expand your polyatomic ion list, even though it's not explicitly written. And so we just told you to hone in on all of the chlorine ones. Take a look at your chart. It probably has all of the variants with chlorine. And what I mean by that is it probably has chlorate, chlorite, hypochlorite, and perchlorate. There is a reason for that. They are very intentional prefixes and suffixes. And if you'll notice, the only difference between them are the amount of oxygens. So let's fill them in. Chlorate is ClO3 with a charge of -1. Chlorite is ClO2 with a charge of -1. The only difference is I lost an oxygen. Hypochlorite is ClO with a charge of -1. So it once again lost an oxygen. You can kind of guess the pattern here, even if it's not right in front of you. Perchlorate, you guessed it, we gain an oxygen. And so the way I think about this is when the suffix ends in ate, that's sort of like home base. And what it really translates to is oxygenated, like proper amount of oxygenation. If it ends in ite, that means less than oxygenated. And then the prefix hypo means much. So this would translate to much less than oxygenated. And per would be more than oxygenated, that sort of thing. Well, this pattern actually correlates to all of the polyatomic ions that you can see. So even if they're not written on your chart, they're still out there. So let's take one of the more common ones. For example, nitrate is NO3 with a charge of -1. And another very common one is nitrite, which is NO2 with a charge of -1. However, hyponitrite and pernitrate are not very common. Therefore, we can still extract them. And you might be saying, oh, well, all you got to do is look at the oxygens. If it ends in 8, it always has 3 oxygens. Per blank 8 is always 4 oxygens. Not quite. However, it's very simple because all of the 8 forms of the polyatomic ions, the common polyatomic ions, are on your list. So let's look at sulfate, for example. Sulfate is SO4 with a charge of -2. So we've got a little wrinkle in what some of you might have been thinking just a second ago. But the pattern still applies. If sulfate is SO4 with a charge of -2, what would sulfite be? Just subtract an oxygen. Don't do anything to the charge. The charge stays the same. So then hyposulfite is going to be SO2 with a charge of -2. And persulfate is going to be SO5 with a charge of -2. So if you think about it, you can actually do this to all of the polyatomic ions. Carbonate, phosphate, all of the really common ones that are probably on your list, they're out there, and you might be expected to utilize them. So let's look at some of those more difficult examples to close out the day. All right, so first off, we're going to go from the formulas to the names of these less common tertiary acids. And so what I left up is that reference point that we just consulted upon. We kind of made a little table out of over here, and it's going to help us in this endeavor. So BRO is the gang that we're attached to. That's what we care about. And if you're looking at a polyatomic ion sheet, it's probably not there. However, one that could be there is not BRO, but BRO3 could be there. And if you find him, that's bromate. And if he's not there, you know who is there? ClO3 is there. And what did we say about all of the halogens? They can be used interchangeably. If chlorate is ClO3, then bromate is BRO3. If you want to extend this even further, BRO might not be there, but you know who is probably on your list? Hypochlorite is ClO, which would mean that hypobromite would be BRO. So what we just did with this is we determined what the name of our gang is. It's hypobromite. And because it ends in ite, that tells us what our acid is going to end with. I ate something icky, so I drank Sprite because it's delicious. So the name of this guy becomes hypobromous acid. So we can use different reference points on the polyatomic ion sheet to get us there. And so we're going to erase these to do our next one. So the gang that hydrogen is attached to here is CO2. Looks just like carbon dioxide. The only difference here is that it has a charge of -2, so it's not carbon dioxide. It's a polyatomic ion. Now, I don't see CO2 with a charge of -2 on my chart. But what do we see? We see carbonate. And if carbonate is CO3 with a charge of -2, what would it be called if I take away an oxygen? All you got to do is go down on the chart, and it goes from carbonate to carbonite. If you're a Star Wars fan, you know, okay? So, this becomes carbonite. It ends in ITE, which means the name of this acid becomes carbonous acid. Kind of sounds like you're getting a sweet bonus deal. Carbonous acid. So now let's consult our last example here, HFO2. FO2 is probably not on your chart. However, chlorine and all of its variants probably are. And keep in mind, fluorine is also a halogen. So FO2 might not be on there, but ClO2 probably is. And ClO2 is chlorite, which means FO2 is going to be called fluorite. And so this one also ends in ITE. So the name of this guy becomes fluorous acid, like so. Now we have our final three examples in the notes: iodic acid, hypocarbonous acid, and hypoiodous acid. Now we're going to use the same patterns before to find the formula from the name. So what I'm looking for here is a gang. Because the suffix of this acid is -ic, I'm looking for a polyatomic ion that ends in -ate. Iodate is not on my list. Oh my goodness. But iodine is a halogen. And iodate might not be on the list, but you know who is? Chlorate. And if chlorate is ClO3 with a charge of -1, then iodate is IO3 with a charge of -1. Like so. And so we're going to crisscross our charges here. They both have charges of 1. Where should we do this? Let's just do it above here. And so, HIO3. All right, on to the next example. Hypocarbonous acid. It ends in us, which means I'm looking for a gang that ends in ite, so I'm looking for hypocarbonite. That's not on my list. But you know what is? Carbonate is on my list. And how do I go from ate to hypo-blank-ite? Well, lose one oxygen, lose one oxygen. So, hypocarbonite is just CO 2-. We're going to crisscross our charges with that hydrogen. And we get H2CO. In our very last example, hypoiodous acid, it ends in us, which means the gang ends in ite. All right. I don't have hypoiodite on my polyatomic ion chart, but you know what I do? Iodine is a halogen, and I definitely have hypochlorite on my chart, which means hypoiodite is IO minus. They both have charges of 1. Crisscross them, and we get hyo.
Ladies and gentlemen, thank you for exploring chemical nomenclature with me. What a blast this has been. I hope you've grown as a human being. I hope your brain is just a little more wrinkled. Okay? Join us next time as we explore chemical reactions. Wow. Stay safe out there, people. I thought I'd try to do my own musical soundtrack this time, so please leave a review.